Tapelo SZ here again. So today we're still doing the 2023 Gauteng Prelim paper 2 physics or chemistry, right, to be exact. And this is the multiple choice question, Gauteng. Okay, so this was happening here. So right, so we just need to choose between A to E, wara, you know, these are the instructions. Just make sure you read them. Okay, right, so we only write down the letter. So 1.1. So it says the empirical formula of hexanoic acid is, remember, look at this, guys, they even made it bold. Empirical formula. So empirical formula is the simplest whole number ratio, right, of the elements in a compound. Ratio of elements in a compound. Okay, so what we need to understand is that if we had C18, V3, V8, let's just make it even numbers, plus T for Tapelo, T7, not T7, let's just say T14. Okay, so what this means for us is that this is the actual compound, CVT, okay? But the empirical formula will be the simplest whole number ratio of each of the elements in the compound. So what this means for us is that we need to find a common factor that we can divide by Kaufel, okay? So here we're going to have 9, dividing each thing by 2, 9, 4, 7 for T, okay? So this is the empirical formula. So it's the simplest whole number ratio of elements in a compound. So the simplest. So what happens here is that they give us a couple of options, but let's just draw this thing. It's what's hexanoic acid. So hex 6, 1, 2, 3, 4, 5, 6. I know that I'm going to have a double bond there and an OH, right, representing the acid, the carboxylic acid. 1, 2, 3, 4. You see, I'm just making sure that everything has 4. Just make sure you count, okay? Carbon has to have 4. So now what I see, what we can see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so what we have indeed is 6 carbons, obviously, and then we have 12 hydrogens. That's what we just counted now. And then how many oxygens do we have? We have 1, 2 oxygen. So this is O2. So what this means, this is the actual compound itself. Okay, but now what we're looking for is the simplest whole number ratio, which is the empirical formula. And then if we divide everything by 2 this side, we're going to have C3H6O. Okay, so this is the empirical formula, and which is what? Option D. So 1.1, we take D, and then we move on. So now 1.2 says, which intermolecular forces are present between the molecules of C7H15 CHO? Okay, so let's just be safe. Let's draw this thing. Okay, let's not think about it too much. Let's draw, and then we count, and then we see which one is which. So let's see, C7. So that's a penti. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, so let's just fill in the hydrogens where we can. So it's 1, 2, 3 hydrogens, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have to stop there. So let's just join the carbons first. So we have 15 hydrogens that we put outside. One. But now then they tell us that we have what? A HO. So we have another H. Ne? And then we have an O. But the O can't just. So it can't just exist. So this is OH, in other words. Okay. So what we can see here is that we have an alcohol, right? And remember that an alcohol belongs to an alcohol belongs to the hydrogen bonds. Okay, so it belongs to the hydrogen bonds, but it only has one side of bonding. But the main thing that we need to understand is that in London forces we have all organic compounds. So all organic compounds have these London forces, and then in dipole we have all organic compounds except the alkanes, alkynes, and alkenes. Okay, so those are the only ones that we don't have in the dipole. And then in the hydrogen, we only have 2, exclusively 2, which is your carboxylic and your alcohols. So what we see is that this alcohol that we've just drawn here has everything, right? It has this, that, and that. So it has the London, the dipole, as well as the hydrogen bonds. So it does not only have hydrogen bonds, it has everything before it, but it's special, right? Along with carboxylic acid, they just belong to all of them. Okay, so let's just understand that. So that's how structure is made up. So our answer is going to be dipole, 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 dipole. We're looking for everything. So this one is saying only dipole, dipole, right? Not even, doesn't have that alone. Then it says dipole, dipole forces, dispersion London forces, and hydrogen bonding forces. This is the one, okay? It's the one that has everything, and then obviously C is just limiting it, and then this is also limiting it. Okay, so let's go 1.2. Let's choose B. Okay, let's see. Okay, and then let's talk 1.3. It says the structures of 4 organic compounds are shown below. Then it says which compounds will decolorize bromine water. So bromine water, so Br water, right? It can undergo two reactions. So obviously it can move from bromine water, right? It's a haloalkane, okay, or yeah, whatever it is, okay, and then it can move to something that is has single bond, but that is saturated, I meant to say, or that is unsaturated. Okay, so what this means to us, it means that if we're moving from something that is saturated to saturated, this is substitution. Okay, and then the other one is elimination. Okay, so what this means for us is that, yeah, it will move from saturated to unsaturated. And with it's called the bromine water test. It's somewhere on YouTube, you can check it out. Okay, so what that means for us is that here, if it goes through substitution, which means it does single bonds, it'll move, right? Because bromine water is naturally brown, so it will stay brown. It will stay brown in saturated. So if it's moving from single bond to single bond, it will stay brown. Okay, and then when it moves from unsaturated, it will move from brown to colorless, right? Colorless. So remember, unsaturated is like a double bond, okay, or a triple bond in that matter. But in this case, we don't have any triple bond. So now we can see that this is compound 1. Compound 1 is an it's a carboxylic acid. It's a carb acid. And then this one is an alkene, right? So this is the one that we need to take care of, that we need to watch out for. And then this one is also an alkene as well. So this one is just, an alkane. But it says which of these compounds will decolorize bromine water fast? So it has to be 2 and 3 because these are the ones that are unsaturated. Okay, so unsaturated. Oh yeah, so it's 2 and 3, compound 2 and 3. Hope you understand why I chose this option. Okay, so we are saying it's 1.3. The answer can be B. Okay, that's what I see. And then it says which one of the following best explains the role of a catalyst. So let's not even look at the question. What is a catalyst? A catalyst is it's a substance that it provides an alternate path, right, for a reaction to take place, and it also lowers the activation energy. So they're saying which one best describes. Before we even go there, we have to define it on our own and see what matches. Let's not look for the answer here, versus the definition here. Okay, so it says it lowers activated complex. No ways. Activated complex is different from activation energy. So it increases the concentration of the reactants, and therefore increases the rate of reaction. No, it does not increase the concentration of the reactants. That's cap. Okay, and then it says it provides an alternate path with lower activation energy. Okay, I like this one. Okay, then it says it increases the net activation energy. No, it doesn't increase activation energy. It in fact lowers it. Okay, so our answer for 1.4 can be what? Can be B again. If you know that thing when you have B. Okay, let's see. Okay, so the next one says, okay, the energy distribution for a fixed mass of gas at 2 different temperatures, T1 and T2, are shown below. So this is Maxwell-Boltzmann's curves, right? Distribution curves. Okay, so it says which one of the following is the correct interpretation for the curves for the temperature change from T1 to T2. So what we need to understand here, if we zoom in on this curve, what we'll notice, right, is that this one, okay, this one, a T2, this one that has to do with T2, let me just change the highlighter and just to make it, so we can see that this guy, T2, one, has a higher, has more number of particles after activation energy. So this is EA, remember, ne? So after activation energy, we can see that T2 is the one that has more. So the one that has more, right, it means that it's the one that the temperature is higher. So what we are saying here in essence is that T2, the temperature of T2 is higher than the temperature of T1. That is the fact, okay? According to that guy. Yes, according to collision theory, I meant to say. So that's what's happening there. So T2 is higher. Even though the graph is lower here, there's a lot of explanation into that, but its energy, or its number of particles after the activation energy is more, okay, than T1. That's why we say T2 is greater, right? Temperature 2. So what happened here is that from T1 to T2, we increase the temperature, because they're asking us from T1 to T2, you increase temperature, okay? So they didn't even ask us any option on the table. It's fine. But we understand that the temperature increased, right? And when temperature increases, so when T goes up, right, the rate of reaction increases. Okay? And yeah, but it's fine. So the number of effective collisions increase, okay? Because the number of effective collisions basically explains the rate of reaction, okay? So we are saying that they increased, okay? 1, 2, 8. So that's what we have there as the possible options, okay? And then here, let's talk about the activation energy. We can see that the activation energy was constant throughout. And other than that, understanding 1.4, which we just did now, the activation energy is only lowered or affected, okay, by the catalyst, okay? So now here we are trying to say that activation energy stays the same. So we can see the one that we ticked, that ticks our boxes, is this one, A. So let's go for 1.5. We have A, okay? Alrighty, let's go to 1.6. 1.6 says each of the reactions represented below is at equilibrium in a closed container. Which of these reactions will an increase in pressure favor the formation of products? But before we even look at those, let's understand something. When increase in pressure, this guy, I think it's a chartelie, okay, one of my proofs, okay. So it says an increase in pressure, right? He says an increase in pressure favors the reaction with fewer number of moles. So they spoke about pressure. We don't even want to answer the question yet. Let's go talk about this fewer number of moles. Let's go find out the number of moles of each, right? And by the number of moles, I mean the balancing coefficient, not like using concentration and volume and whatnot. But okay, so it favors the reaction with fewer number of moles. So we're talking about pressure. Let's go, before you even answer, before you even know what they're asking for, let's go calculate. So here we have 1 mole of that guy. Here we have 2 moles of this guy. So sorry about that. So here we have 1 mole of this guy, and then here we have 2 moles of this guy. Here we have 1 mole of this guy, okay? But here together, here we have 2 moles of products, okay? Here we have how many? We have 4 moles of reactants, and then here we have 2 moles. So we just look at the balancing coefficients, and yeah, we hlanganis. And then here we have 2 moles of these guys, okay? So 1, 1. So here we also have 2 moles. So now let's understand something. We said that the increase in pressure favors the side with the fewer number of moles. So let's go talk. Let's talk. So here, let me just use a different color, okay? So here, what that means for us, it favors the side with the fewer number of moles. So what? This side is favored. And then this side favors the side with the fewer number of moles. Also, this side is favored. So now, C says it favors the side with the fewer number of moles. So here we have 4, we have 2. So this one is favored. And then here we have both. So none of them are favored. Nothing will impact. Not even an increase in pressure too much can affect this one, because they have the same number of moles. So now let's understand something. Let's go read the question. Then it says, which by increasing the pressure will favor the formation of products. So remember, products are on the right. So it means the reactants need to make products. So we can see that the only thing that's giving us products, that's favoring the right-hand side, is C. We can see the others are pointing left, and the other one is not even pointing anywhere because it has the same number of moles. So this one, it can go to C, I believe, okay? So C is the one, okay? Is the one, right? So now the next question is 1.7. It says, consider beakers A and B as illustrated below. Okay, so now what we have there is 200 centimeter cubic of 0.25 mole per decimeter cubic of sodium hydroxide. in beaker A, and then we also have the same in beaker B. We also have the same sodium hydroxide. That's important. That's important. The same thing. So if I add you and me and we are the same, it means I'm increasing myself, or we're increasing ourselves, and we'll see why this is important. Okay, and then it says 20 centimeter cubic of the NaOH solution in beaker A is added to the NaOH in beaker B. So it says, which of the following represents the calculation for the concentration of Na plus ions in the beaker? All right, so let's understand something, guys. Remember that concentration, right, is equal to number of moles over the volume. But they're saying in beaker B. And remember that beaker B is made up of itself, right? Itself. That was already here. This is beaker B. Let's just say this is beaker B. The beaker B type of thing, okay? And then now we added something. We added a few, right, of this guy in this guy. So this guy was raised here. And we poured some stuff, right? So we poured only 20 centimeter, 20 centimeter, not in length, but in the volume, okay? 20 centimeter cubic of that guy. So we didn't pour everything of this guy, no. We poured 20 centimeter cube of him, of that guy that we had, and his concentration was 0.25. So let's understand something, guys. We need to understand that we are adding something on another something. So here we already had 150 centimeter cubed, right? And then now we add 20. So our total in beaker B, right? We have what? We already had 150, but now we are adding 20. Okay, plus 20 centimeter cubic, which gives us 170. Okay, so in beaker B now we have 170, right? The reason we're calculating for the total in beaker B is because they're asking for the concentration of ions in beaker B after that thing was poured. Okay, so now this is what we have here. Obviously this is in centimeter cubic, and let's be civil. This is what? 0.17. We divided by 1k so that we can have it in what? Decimeter cubic. Okay, so that's what we have there. So if we're to calculate anything, this is our volume, right? So without even going further, we can see that this option and this option is cancelled out, because we know that concentration is number of moles over volume. So these ones with 0.15 at the bottom, we can't be even looking at them, because we are looking at what is in beaker B after that guy was poured in. Okay, so we already have like 50% chance of getting our answer. Okay, just from that. Okay, now let's move on. So what we need to understand is that we have the volume sorted, but now we need the number of moles. All right, so remember we are pouring 20 out of this 200. We are pouring 20 of that in here, so we need to calculate the number of moles of what we are pouring. So the number of moles obviously is equals to CV. So this is the concentration. Like even if I take small of this guy, the concentration of this guy will never change. So even if like I have Oros, if I give you 2 spoons of my Oros, the concentration is still the same. It's just that the volume is different. Okay, so the concentration is still 0.25, but I'm not pouring the whole 200. I'm pouring only the what? 0.02, which is 20 cm3. Remember, we need to divide by 1k. So I believe here we're going to have 0.005. Yes, I think so. Okay, just confirm there. Right, so 0.005, that's what we're going to be having there. Okay, we are adding this number of moles to this guy here. But how many number of moles did we have already here? We had 158. Number of moles is equal to CV. Okay, but the concentration here was what? 0.1. And then our volume here, remember, we already had what? 0.15. The reason I'm saying 0.15, I'm taking that centimeter cubic, I'm dividing it by a k, right? 1k, and this gives us 0.015. So what this means for us is that the total number of moles, we can add the number of moles because it's the same thing. Remember, it's the same thing. It's NaOH and also NaOH. So we are allowed to add these two guys here. So we're going to add 0.005 plus 0.015 as the total number of moles. Okay, and then obviously our volume is this guy here. So now let's see for the option that gives us that. So it's A. This one is 0.05. Can you see? There's 1 0 here, and we calculated it what? 0,005. And it's important, guys. The reason they put that option there is because one person may identify that, oh, the volume is very 17. Okay, sharp. But now they might use this 200 here. And remember, we didn't take the whole 200. We take only 20 centimeter of it. And then we put it that side. And if you use the 200 there, your answer would have been B. Okay. So let's just make sure we watch out. Okay. And then let's move on. So 1.7. Our answer can be A. All right, let's just move on. And then it says, when a galvanic cell delivers current, the purpose of the salt bridge, right? Salt bridge has many purposes, right? So it does not allow electrons. No, it allows ions to move. So this one is I. And then it ensures electrical neutrality. That's true. And then it prevents two solutions that from mixing. Not quite. Okay. And then it says allows electrons. It doesn't allow electrons to flow. It allows ions, okay, to flow, right? And also electrons don't flow from cathode to anode. Electrons always flow from the anode to the cathode. So yeah, this one is the statement. Okay, so it prevents the two solutions from mixing. It could be, but I think the one that is most correct, the one that I think like is the most correct, is this one. Ensures electrical neutrality. Okay, so let's say 1.8. Let's go with B. Okay, and then 1.9. It says, which of the following is the strongest reducing agent? So we have Ag, zinc, nazeng, and copper, and Al. Okay, so let's go just identify them. So we already identified Zn and Cu when we were calculating, which is the one that I highlighted in blue. And then let's go to Ag. I think it's 0.80. It's only 0.8. Okay, and then we have Al, aluminium. Okay, so is Al. Yeah, it is, right? So this is the one. So now they're asking which one has the strongest reducing agent. Remember, this arrow told us which one is about increasing reducing ability. So the one that is at the bottom is the one with the strongest reducing ability, which is obviously the Al. Okay, so let's move on. Let's do fast. Okay, so 1.9, we have Al, which is option D. And then here, let's talk about this one, 1.10. It tells us that the gaseous chlorine is used to disinfect water in public swimming pools and react with water according to the following balanced equation. Okay, sharp. So now we can see that something is happening here. So we're taking chlorine, right? It disinfects the swimming pools. Okay, and then H2O, and then it gives us something with an acid. HCl is a strong acid. Okay. So what this tells us is that even like when you're swimming, for those of us who can swim, when you swim, I almost drowned, but it's fine. So when we swim, we always like if the pool is disinfected, right? It's this blue color that you see there, right? It's very, very acidic on your eyes if you open your eyes while you're inside. Okay, so those ones that are cleaned, right? Those proper ones, they always have this blue color, and it's sort of acidic. If you open your eyes, right, it's acidic on your eyes. So maybe this explains it. Okay, I don't know, but it says that the addition of chlorine gas changes the pH of water. So we'd assume that it changes it to a lower pH, because we understand that acidic pH ranges from 0 to 7, just before 7, and then the basic pH is after 7 to 14. And then it says which of the following substances must be added to public swimming pools to periodically increase the pH. So what this means to us is that the only thing that we need to understand is that 0 to 7, this is acid, right? And then after 7, right, from 7 to 14, and from 7 to 14, that's basic. So we need to understand that this thing already is a strong acid, so it means it has a very low pH. Okay, so now we want to increase the pH. The only way we can increase the pH, I believe, it's by adding a base. Okay, so if we add a base, the pH may increase. Okay, so what that means for us is that let's look for a base here, I'd assume. All right, so please let me know in the comment section which one you chose or which one you would choose just by reading the question. Okay, so what we need to understand is that we need to identify, okay, some stuff. So let's see if we can have a base in the options here so that we can increase our pH. So obviously this is an acid. This cannot receive any more protons. There's nothing such as H5Cl plus. I haven't seen that. At least I haven't seen that. Okay, and then this one is obviously an acid. because we understand that it can donate a proton and become NH3Cl-. It's possible for it to be that. So it's an acid. And then this one, sodium carbonate. We've once seen sodium hydrogen carbonate. So this happens, sodium hydrogen carbonate, in one of the past papers. So this one, it can obviously accept a proton. So this one is a base, but it's a very weak base. So I think weak base is going to do it small by small, which is periodically, maybe. Okay. And then here it says KCl. Let's why salt. I believe it's a salt. Okay. And then we have this one is a strong acid. So the strong acid, if I add a strong acid, I can't increase the pH. It will only decrease the pH, but I can't add salt. Right? Salt, yeah, right. But I think it's arguable between B and C. Okay. But I think the one that's most correct in this perspective that I see it is B. Okay, so 1.10 we can go with B because that's the base and that's the one that will increase the pH to, you know, from that very, very low acidic pH to something around neutral or maybe even basic, right? But we doubt it's going to be basic because we doubt it's going to be fully basic because this is a weak it's a weak base, right? So it can periodically increase the pH, right? So yeah, so this was the multiple choice question of this paper. I hope, you know, maybe we understood some stuff, and yeah, man, you know, so you can just share with your friends and then just let me know what you think in the comment section if, you know, you want me to do the rest of the paper or, you know. So yeah, let's talk. Message me on 06081 309 4512, okay, to discuss school stuff there. So yeah, this is the thing, and then yeah, you can discuss your views and then let's talk. If you want the question paper, just text me, and then yeah, let's talk, let's share views, and yeah, school stuff only. Thank you so much.